Okay, so let's begin. So this is just review questions for your quiz 3 coming up. And the first one is from a book. Now, I've forgotten what the name of the author or the book was. I just, in a bit of a rush, looked at the relevant page, and so I'm going to talk about what's in there. Okay, so this is titled Completing the Square for Matrices. All right, now I hope everyone knows how to complete the square for quadratic polynomials. All right, so what we have here is we have a matrix M, and we're going to suppose that it's got real entries, it's a square matrix, and it's size D by D. We'll also assume that's symmetric, invertible, and we will assume that X, and I've got an uppercase B here, just to be sure that I don't confuse us with the subsequent problem, right? Because we also need a B in a subsequent problem. Okay, so X and B are vectors, or just a column matrix, if you like, of length D. Okay, so we've got to basically show that these two lines are the same, or left and right are the same, right? And so I've kind of compressed it a little bit in saying where Z is equal to X minus M inverse times B. Okay, so we've assumed that M is invertible here. So otherwise, this is a little bit lengthy, this part of it. And so I wanted to be able to fit it all there. Okay, so this is what we're going to do. Now, the way we're going to approach that is first considering parts of the right-hand side. So in other words, I'm just looking at this little bit here, and let's expand that, and then we'll come to this line at the end. Okay, so starting with this one, so that's Z transpose times M times Z. Okay, so I just sub in what I've laid out there, X minus M inverse times B, and so that is transposed there, times M, and times the same thing, but not transposed. Okay, so subbing in. Okay, next, I want to apply the transpose inside the bracket, and I can just do that, right? Because this is a sum of two column matrices, right? And so I can just apply that transpose inside the brackets. And so that's our first step. Apply it inside, okay? And so you can see that's just what I've done there. Now, next, we want to evaluate sort of what this is, right? Okay. So now I can do this, right? I just have to think for a moment. That is a legal thing to do. Okay, so yeah, I'm pretty sure I can do this. Okay, so I swap them around. So in other words, A, B, all transposes, B transpose, A transpose. And then, so that's just that. And then next, what we want to do is start expanding this out. Okay, so what I do first is I bring in the M to this one. Okay, so I expand this M over this little bracketed expression. And so we have mx, and then M times M inverse is obviously the identity. And so that's the identity times B. And so we just have mx minus B for this part of it. And then over here, we still have the same thing as we had in the line above it. Okay, now we can expand the whole thing because we just have, well, two things multiplying together. And so we expect to get 4 terms out of this when we expand, right? So let's do that. All right, so first we have X transpose times MX, and that is right there. And then I take X transpose times that minus B, and I put it right there. Okay, now I deal with the next part, minus B transpose M inverse transposed, okay, times each of these 2 terms. And so we have minus B transpose M inverse transpose times the MX, that is there. And then finally, we need this one times this one. And so that'll be a plus, won't it? Because we have 2 minus signs multiplying. So that's plus B transpose M inverse transpose times B. All right, so yes, we've got 4 terms. That's good. Next, what we want to do is add 2 terms that are like. Okay, so to see just how that's possible, let's see. So remember M is symmetric, right? So that means then that applying that transpose, so we can swap the transpose and the inverse, right? And so we can put the transpose inside and the inverse outside the bracket. But M transpose is just M, right? Because M is symmetric. So really what we're looking at in this and in this is just M inverse. Okay, so then this one should become minus B transpose times X, right? Because this part is just the identity matrix. All right, so that's right there. And then likewise, this here is just M inverse transpose or M transpose inverse, but again, M is symmetric. So this is just M inverse there. So B transpose M inverse times B. Okay, now we've got 4 simpler terms, but these 2 here are like terms because, now, I mean, they look quite similar, right? But the one on the right here is the transpose of this one. However, these are just scalars with a bracket around it, right? Because it's a product of a column, transpose times a column. So we just end up with a scalar for each of these. So these 2 are the same for that reason. So we can say, well, we have 2 of these. And so let's pick our favorite one to say that we have 2 of. And so we'll just go say that's minus 2B transpose X. Okay, and so we end up with 3 terms now. All right, so now let's go and compare this with the this that we're trying to prove. And so what we want to do is we essentially want to take this one on the far right. Maybe you can't see because of this buttons on the screen. But the one on the far right, we want to take that over to the left-hand side of this so that it's the same as what we have here, okay? And then we want to compare this with what remains. And you can see that they match, right? Okay, so we've essentially proved it. So the last line is just to state that, all right? Okay, so that's that part. Let me have a peek at the time. Maybe should accelerate because there's quite a lot of this sort of tedious calculations to look at step by step. All right, next page. Now this says consider the least squares minimizing of this. Now in brackets I've got not the same B as the above B, and that's why I put an uppercase B for that one, right? Because I want to use that result in this. And they're not the same B. Okay, so we're basically going to use the previous formula to express this, and it should involve the pseudo inverse of A, okay? As you know, that least squares relates to the pseudo inverse. Okay, so first step here is to express this, the square of the norm of AX minus B as AX minus B transposed times AX minus B. And then we want to apply the transpose inside and expand. Okay, so here we have X transpose A transpose minus B transpose times AX minus B. And then we just expand and we'll have 4 terms next. Okay, so expanding that, we've got X transpose A times X. So that's that one times that one. And then we've got this one times that one. And so that gives us this. Okay, so that's this times that whole right-hand side expression. Then we have minus B transpose times this first one, AX, which we put there. And then minus B transpose times minus B, and that gives us plus B transpose B. Okay, so 4 terms. Now, we can note that AX is a column matrix, right? And so B transpose times AX times B should be a scalar. And likewise, X transpose A transpose B will be a scalar because it's just the transpose of this, right? So also, these are they the same? I think so. Okay, but they're both scalars. Okay, sure. So now noting that those are the same, And we want to express in terms of this one because they are the same and scalars, so we can do that. So now we compress that to 3 terms. So we've got X transpose A times X, and then minus 2 of these, and still plus B transpose B. Okay, now that we have that, let's take some note of some of the things that we have here. Okay, so we've got an A transpose A, so I want to emphasize that and put it in brackets. All right, and likewise, we've got an A transpose B here, transposed, all right, which is right there. And then this one just carried down. Okay, good. So now this is going to act as our M in the last formula, so the completing the square formula that we did on the previous page. And likewise, this A transpose B is the B of that same formula on the previous page. Okay, and so let's see, perhaps I should bring that up and remind us. I'll have to just fold it in half here and then present it above so you can see what we're up to. Okay, so here, that if I'm using this as the M, I'm looking at this and I've got a minus 2, and here's my uppercase B, you see, and then I've got the X. So this part of the expression we can replace with the right-hand side here, okay? But we've got to be very careful because it's a big mess, essentially, right? Especially when you've got this term involved. So that's what's going to happen next. Right now, at this point, I'm fairly glad I chose to show you what I've already written when I wasn't speaking, because I'm kind of bad at speaking and thinking. Sadly, okay, for me, I guess, but it's all okay. All right, so we basically sub that stuff in, right? So we use the formula, and it's all right here, right? And so you can see we have a rather large expression to deal with. Okay, so, but I put in red below what we have. So this here, this part of it is the Z transpose MZ. That's right there. All right, now this next part is the minus B transpose M inverse B. All right, so I've got that in red, what I'm talking about there. And then this one is just carried from there. Okay, so now that we've got all this, the next step is to deal with all of that, right, and simplify it. Okay, so I'll scoot this up so we're not staring at a lot of hieroglyphs at once, just as least as possible. Okay, so we want to simplify this. So now we've got to identify a few things. Let's see, so I'll see if I can do this now. So here I've got the pseudo inverse, right? But that pseudo inverse is all of this, right? So A transpose times A inverted times A transpose, so that should be our pseudo inverse. And then we've got the lowercase b there, that is there. And then it all got transposed. So that's a little bit more concise now, okay? We still have the A transpose A there carried down. And then this one here is X minus the pseudo inverse of A times B. And then this stuff, I think, is just carried down. And then B transpose B. Okay, now simplifying this, we can now say, let's let P be equal to this expression, right? And that's called the projection matrix. Okay, so now that allows us to simplify this little piece here, right? Because we've got A, and that, and that, and that. Okay, we're just going to call that P in this expression, so we can make it a little bit smaller. Okay, continuing on. So now, finally, we can take this last little piece of it, turn this around, right? So we put the minus in back, and then factor out the B transpose on the left, factor the lowercase b on the right, and so we end up with B transpose in brackets, identity minus the projection matrix P times B. Okay, so this got a little bit better. And so that's now expressed in the appropriate way, okay? So we've got this in terms of the pseudo inverse and the projection matrix. All right, and remember this is the square of the norm of AX minus B. Okay, so I think I'll just write that there. All right, good. So I think I can have a look at the third page. All right, so the next one says, show that A transpose A is positive semi-definite. So what we need to do here is just show that for all X that are column matrices with real entries, that X transpose A times X is greater or equal to 0. So that's just the definition of positive semi-definite. Okay, so what we do then is make a note that X transpose A times X is, now we just move the brackets, right? Because this is associative. The multiplication is associative. So we move the brackets around these two, and then we note that that's AX all transposed, okay? So we have this here, AX transpose times AX, and now we just note that that is the square of the norm of AX, right? And so this, the norm is a number, right? It's a real number. So what we have here is the square of a real number, and so we know that that's greater or equal to 0. Okay, and so that's complete. So that shows that A transpose A is positive semi-definite. Okay, moving on. I think we're okay for time. All right, so next question. What are the eigenvalues of I minus P, where P, again, is this projection matrix? All right, so part of this you've done in lectures, but so given what you've done in lectures, it makes this task a little simpler. All right, so what we want to look at here is, because we're taking eigenvalues, right? So eigenvalues of this matrix, so we want to look at the determinant of I minus P minus lambda I, where lambda is our eigenvalue, or multiple, one of many eigenvalues, right? And we want to consider this expression equal to 0 and basically solve for lambda. So that's how you find eigenvalues. All right, but let's just expand what this is. All right, so expanding this out. So here's our matrix. So this is just minus P, and I really didn't need to sub that in, right? Could have just left it as minus P. And then we can express the rest of it, the part that goes with the i's, as minus lambda minus 1 times I. Okay, so really this tells you that if you know, essentially if you know the eigenvalues of P, then you know the eigenvalues of I minus P, all right? Because of this, you can just basically subtract 1. Okay, provided that you note that the eigenvalues of P are the same as the eigenvalues of minus P. All right, so, and now I've just called this one mu, right? This one right here, lambda minus 1, I've just said, let's call that mu. So this is the determinant of minus P minus mu I. Okay, so mu are the eigenvalues of minus P. And so we've got this relationship between mu and lambda. Okay, but it's important to note that the eigenvalues of minus P are the same as the eigenvalues of P. All right, because you just basically, to compare, you pull out a minus 1 to the power of n in your expression for the determinant. And then since you have an equation equal to 0, you can just multiply through times the minus 1 to the power of n and make it basically go away because you've got 0 on the right-hand side of the equation, okay? So yeah, so the eigenvalues of minus P are minus the eigenvalues of P. And so since in lectures you worked out what the eigenvalues of P were, in other words, just 0 and 1, so now we just multiply this through by minus 1, and so we get 0 and minus 1. All right, and finally, we solve this equation here. This one right here, mu equals lambda minus 1, just one at a time. So starting with 0, so 0 equals lambda minus 1. So this gives you lambda is 1. Okay, and then the next one, minus 1 equals lambda minus 1. So the minus ones vanish there, and you get lambda is 0. Okay, so we've deduced then that the eigenvalues of I minus p are just 0 and 1. Okay, all right, so I think I'm happy with the amount of time that I took, but I'm not quite done because there's a little bit of Julia code to go with this exercise. So I'll just present that to you here on paper. All righty, so this is what Yoni's written up for us. And so basically I understand what this code is doing, and so I'll zoom in a little bit on it. So what this code should be doing here is, well, let's just go through it line by line, okay? So we first introduce the appropriate packages, so using random and linear algebra. And then we call on a seed, or we set up a seed, okay? So if you put in a particular number there, that will be a seed for your random number generator. And if I remember right, this allows you to repeat your experiment, right? Because if you're choosing the seed, then the results should be the same, okay? All righty, so then we've got N and M are 3 and 5 respectively. Okay, so then we've got a random 3 by 5 matrix is A, and B is a random, I guess, column matrix of size M, all right? And so what we get out here is, I guess, is the last one, which is our matrix, or column matrix B. And then X hat is the pseudo inverse of A times B. And then there it's presented. And then here we've got the norm of A times X hat. Remember, X hat is this one. And so that's squared, and so this is the norm. We can see that that's greater or equal to 0. All right, now what have we got here? B transposed times I minus P times B, okay? So that's that one right there. So in other words, the cost of the least squares, this one, greater or equal to 0 because I minus P is positive semi-definite. All right, I'm gonna just turn it over to you now, Walla. If you're ready. Just grab my things. Grab the bag too, in case you accidentally kick, because I got the laptop in there.
No. Yeah, now let's continue. We need to use part A, which Sam proved with you. And now we need to prove that the sum of 2 quadratic forms in X. We have 2 quadratic forms. We need to find the sum of these quadratic forms. We need to expand the first part, and we need to expand the second part. Then we need to add it together. Let's try to expand the first part. We need to expand X minus mu transpose times sigma inverse X minus mu. Here we have a transpose. At the beginning, we need to expand this part, so we can write it as X transpose minus mu transpose multiplied with sigma inverse, and this is multiplied with X minus mu. Now we can expand X transpose times sigma inverse times X. This is the first term, X transpose sigma inverse X. The second term, X transpose times sigma inverse times mu minus X transpose sigma inverse mu. Okay. Then mu transpose times sigma inverse times X minus mu transpose sigma inverse times X, and the last one plus mu transpose times sigma inverse times mu. Mu transpose sigma inverse times mu. Look here, if you look, this part and this part is the same because this is a column transpose times a matrix times a vector. So if you try to find this one and this one, both will give you the same answer. So we can write it as this is equal X transpose sigma inverse X minus 2 mu transpose sigma inverse X plus mu transpose sigma inverse mu. We need to follow the same step to expand X minus theta transpose V inverse times X minus theta. We need to expand also X minus theta transpose times V transpose times X minus theta. This is will give you X transpose V inverse X minus 2 theta transpose V inverse X plus theta transpose V inverse theta. Now we need to add it up, this part plus this part, because here in the question we need to find the sum of these two. So we need to add part 1 plus part 2. Look here, we have X transpose sigma inverse X. Here we have X transpose V inverse X. We can write it as X transpose multiply with sigma inverse plus V inverse times X. So f of X equal X transpose times sigma inverse plus V inverse times X. From here, the middle, also we have 2 multiply with mu transpose times sigma inverse times X. Here we have 2 times theta transpose times V inverse times X. So we can write it as minus 2 multiply with mu transpose sigma inverse plus theta transpose V inverse, and all of this multiply with X, plus here we need to add this one plus this one. This is a plus mu transpose sigma inverse mu plus theta transpose times V inverse times theta. We can write it as, suppose that this is mu, we can write it as this is a mu equal sigma inverse plus V inverse. We can write this as B transpose. So we need to take the transpose for both sides. We can write B here as this is equal sigma inverse, because we need to take the transpose for this part, sigma inverse mu plus V inverse theta, and this is, call it R equal mu transpose sigma inverse mu plus theta transpose V inverse theta. So try now to write it by using mu, B, and R. So we can write it as f of X equal X transpose mu X minus 2 B transpose X plus R. This is the same formula which proved by Sam at the beginning in part A. This is equivalent to, if you have X transpose mu times X minus 2B transpose X, we can expand it and write it as X minus mu inverse B transpose multiply with the mu multiply with X minus mu inverse B minus B transpose mu inverse B. So if you try to analyze this part, we can write it as like what we have here. Just we need to write the same formula. This is equal to X minus mu inverse B transpose mu multiply with X minus mu inverse B minus B inverse mu inverse B plus R. Okay, so this is the sum of two quadratic formula. If you have two quadratic forms, we can add them together and we can find just one form. Okay, this is for part E. Okay, let's have a look to another example. Is it clear for you? Is it clear? Yeah. In part F, we have let f of x and y equal x squared divided by y to power 4 for any x greater than or equal to 0 and y greater than 0. At the beginning, we need to find Hessian matrix, find Hessian of f, and prove that for any xy, this Hessian matrix is positive semi-definite. So at the beginning, we need to find the Hessian matrix. Then we need to prove that it is positive semi-definite. If you try to use Julia to draw this function, you will get here. If you try to use Julia using plot, it's easy to draw. If you try to using plot and the grid from 0 to 2, and each step is 0.1, and here we have the function f of xy. This is the function is given, and we have z. We use the 4x in the grid because we need to split it, and we try to multiply the curve. If you look to this curve, this is a convex function. All the time is going up. This is convex function. Now we need to find the Hessian matrix for this function at the first step. And at the second step, we need to prove that it is positive semi-definite. Now let's try to find together Hessian matrix. In general, to find the Hessian matrix, Hessian is given by, because here just we have x and y, it is the second derivative of the function with respect to x, because here just we have x, the second derivative with respect to x. Here we have the derivative of the function, one the first time with respect to x, and the second time with respect to y. Here we have the derivative, the same thing with respect to x and with respect to y. And here we have the first and second derivative with respect to y. So we need to find the derivative, but here the second derivative with respect to y. Okay, just you need to find these constant, these variables. You need to find, here we have this function. We need to find the second derivative with respect to x. We need to find the first derivative with respect to x and the second derivative with respect to y. And we need to find the second derivative with respect to y. If you try to find the Hessian matrix, you will get that because it's an polynomial and it's easy to calculate the values of the derivative. You will get here, this is 2 over y to power 4. You will get the derivative of this function with respect to x, the second derivative. Here, if you try to find the derivative at the beginning with respect to x, then with respect to y, it is equal minus 8x divided by y to power 5. And here the same thing, you will get also minus 8x divided by y to power 5. And the last thing here, you need to find the second derivative with respect to y, and you will get that this is equal 20x squared divided by y to power 6. So this is the Hessian matrix. Now we need to prove that it is positive semi-definite. Suppose that we have a vector, so we need to prove that if we have a vector, we need to prove that x transpose multiply with Hessian matrix times x greater than or equal to 0. So suppose that we have the vector x, which not equal to 0. Suppose that this vector is x and y. Here we have x and y. Multiply with Hessian matrix. This Hessian matrix is here, which we found it here. This is 2 over y to power 4 minus 8x divided by y to power 5. Here we have also minus 8x divided by y to power 5. And here we have 20x squared divided by y to power 6. And all of these multiply with x and y. Just we need to find the multiplication between these this vector times this matrix times this vector. If you try to multiply these together, you will get that if you try to simplify and multiply these together, this will give you 2x squared divided by y to power 4 minus 8x squared divided by y to power 4 minus 8x squared divided by y to power 4 plus 20x x squared divided by y to power 4. If you try to simplify, here we have 20 plus 2, 22, minus 16, this is equal 6. So this is equal 6, x squared divided by y to power 4. And we know that x squared is a function which is all the time increasing, and y to power 4 also is increasing, and all the time it's positive. So this is positive, and this is also is a positive. So this function is greater than or equal to 0. So this is the way we can prove that this function is positive semi-definite. Okay. Now, let's move to another question. Here we need to look to question 3. In question 3, okay, I will give you the link so you can see this question and the solution if you want. Okay, I will give you the link so you can see this PDF function. This is the PDF file. Okay. Now we need to look to question 3. In question 3, they ask, we consider now the least square problem, where we attempt to solve the linear system of equation A omega equal B. We have this equation, A omega equal B, with A and M times N matrix. They give you that A is M times N matrix, and B is a vector, M vector. Consider the loss function. They give you the loss function given by L of omega equal the norm of A omega minus B to power 2, where the norm is the L2 norm, and we are seeking omega that minimizes L omega. Now we need to find the point which minimizes this function. In part A, they ask, explain why the minimizer of L omega is the same as the minimizer of the norm of A omega minus B. We need to prove that the minimizer for L omega is the same as the minimizer for the norm of A omega minus B. Let's try to solve it together. In question 3, part A, okay, they give you that omega equals 0. This is given. And they give you that A is a matrix, M times N matrix, and B is a vector, M vector. B is an M vector. And they give you that L omega equal the norm of A omega minus B to power 2, and we are in L2 norm. We need to explain why the minimizer of L omega is the same as the minimizer of the norm of A omega minus B. Now, the solution. Suppose that the point which minimizes this function, call it omega star. So at the beginning, suppose that, or let omega star is the minimizer, the point which minimize the function L. So because it's the minimum point, so if you try to substitute in this function, so L of this point, okay, less than or equal L of omega for all omega belong to Rn. This is the first step, okay? Because we suppose that omega star is the minimum point. So L of this point is less than or equal L omega. Okay. Now we have the function L omega. We need to write this function as the multiplication of two different functions. Suppose that L of omega, we can write it as G of f of omega, where f of omega equal the norm of A omega minus B, and G of U, call it, this is equal U squared. We write it as two function, G of f omega. This is the first step. Look here, if you look to f omega, this is a norm function, and the norm function all the time greater than or equal to 0. It's positive. This is greater than or equal to 0. And also if you look here to G U equal U squared, And this function is a monotonic increasing function. This is a monotonic increasing function. And also is a continuous. Because if you try to draw u square, all the time it's a continuous function, and also all the time it is increasing function, okay? So we can find the inverse of this function. So we can find G inverse. So because it's a monotonic function, it's an increasing and continuous function, we can find G inverse of this function. So G inverse of this function is exist. Because here G of u equal u square, the inverse of this function is the square root of this function. So G inverse of z equal square root of z. Now let's try to substitute here L of omega star less than or equal L of omega. We need to substitute by using this formula. So we can write it as G of f of omega star less than or equal G of f of omega for all omega belong to Rn. We said that this function G is a monotonic function and it's an increasing function. Let's try multiply both sides by G inverse. Multiply both sides by G inverse, okay, for the function. So we will get, if you multiply this one by G inverse, this will give you f of omega star. This is equal f of omega star less than or equal f of omega for all omega belong to Rn. And we suppose that f of omega equal the norm of A omega minus B. So we can substitute here. This is equal the norm of A omega star minus B less than or equal the norm of A omega minus B. So this is the proof for all omega belong to Rn. So this is show that the minimum point for L omega is the same as the minimum point for the norm of A omega minus B. So we can find it without the square. If you have something with a square or without a square, you can get the same minimum point because we can write it as a multiplication of two functions, and we can multiply this part here by G inverse. The idea here, we can multiply this one by G inverse. So we will get that f omega star less than or equal f of omega. This is the proof for part A. Okay. The last thing we need to prove part B. Okay. In part B, they ask, show that the gradient of L is the gradient of L omega equal to times A transpose multiplied with A omega minus B. We need to prove that. We need to use the same idea. We need to write L of omega as a multiplication of two functions. Then we need to apply gradient descent. So in part B, from question 3, they ask, show that we can write the gradient as that. We need to prove that gradient of L omega equal to A transpose times A omega minus B. At the beginning, we need to write L omega as a multiplication of two functions, F and G, like what we did before. We can write L omega. We can write it as a composition between two functions. We can write L omega as a composition of two functions. For example, we can write it as h of x equal x squared, the norm of x squared, and g of x equal ax minus b. So we can write it as f of x is equal h of g of x. Okay. We can write, suppose that there is two function, because it's easier for us to find the derivative. If you can write it as two function, a composition of two function. Okay. Suppose that g is function from Rn to Rp, and h is a function from Rb to Rq. Okay. Now we need to find the Jacobian of this function. To find the derivative, we need to find the Jacobian of this function. So we need to let the Jacobian of the function f is df. So to find df, the Jacobian here, we can find the Jacobian of this function by using h and g. So we can write it as d f of x equal d of h g of x. We need to use chain rule, multiply with d of g of x. So we need to find the Jacobian for h of g of x times the Jacobian of g of x. And also there is a relation between the Jacobian and the gradient. In general, d f of x equal the gradient of f of x transpose. Okay. And here, the function h, we suppose that the function x h equal the norm of x to power 2. So we can find the derivative of this function, and we can find the derivative for this function. So we suppose that h of x equal the norm of x to power 2. This is the same as the summation of x squared. If you try to find the gradient for this function, this is equal to
times x. Just I find the derivative here. And if I'm trying to find the derivative for the function g of x, which equal ax minus b, the gradient of this function equal a. Just the derivative for the first one and the derivative for the second one. Now just we need to go to the gradient of f of x transpose and find this as by using the gradient of h of x and the gradient of g of x. Okay, so the gradient of L of omega equal the Jacobian of f of omega transpose, which equal the Jacobian of the function g omega transpose times dh of g of omega transpose by using chain rule. This is here by using chain rule because we define here the same thing. df of x, this is equal dh of g of x times dg of x. Just here we multiply everything, take the transpose for everything, okay? Now just we need to substitute. What's the Jacobian of g of omega transpose? We find here the gradient of g of x equal a. So this is the same as the Jacobian of g omega. Just we need to multiply with, take the transpose of this matrix. This is equal a transpose, okay? For the second part, we need to find the Jacobian of h of g omega transpose. And we found here that the Jacobian of h equal 2 times this function, times 2 multiply with g of omega transpose and all of these transpose. Why? Because we need to take a transpose for h and transpose also from here. So this is equal a transpose times 2 times here transpose, it will be the same, and g omega, and the value here of gx or g omega equal ax minus b, and because we are under the function h, this is equal
A omega minus B. So this is equal to A transpose multiply with A omega minus B. So we prove that the gradient of the function L equal to A transpose multiply with A omega minus B. Here we have transpose, it will the same. Just we substitute the value of G omega, and here this is Gx equal Ax minus B. So G omega equal A omega minus B. I put the value of G omega, which equal A omega minus B. Okay. Part 3, if you need, you can look to it, because I will share the PDF file with you, so you can have a look to part C from the same question. Okay. This is what we have today. If you have any question, you can ask. I think the deadline for assignment 2 is today. Please try to submit your assignment if you didn't submit. Yeah. Yes. Yes. Okay. I'm not sure what is finding. Yeah, we need to calculate the storage.
No, that Jeff, that means you need storage this picture in your computer.
Yeah.
How much space to choose?
How can you know that? So you will, I think you calculate So I generate a picture from your computer. Okay. Then in each one, you will get a different storage. Okay. Which has the lowest one, we call it an optimal. Because it doesn't take too much space from which one.
I can't use the force. It's assignment 1. Let's change. No, assignment 2, question 1. Actually, I finished this UQ's lab, but my 2 computers all done work. I really want to know. Yeah.
What's that?
It's good and clear. What do you think?
Your voice was clear. I was kind of on my phone a little bit. So
Yeah.
I wasn't watching the details, but your voice was very clear.
Thank you.
Yeah.
Just me and you.
Okay, sure. If it stays like that, then I think we should just wait until somebody comes in, because the first has been recording. So
I think Jonathan will come.
yeah, now we'll see. We'll wait until someone comes in, and then if and when they do, I guess we'll start then.
Yeah, you sent an email to us.
I did. So I got back to him on the way out the door, basically. Just to basically all I said was that I'll try to get it uploaded as soon as. Yeah. So the recording takes some time to be ready to download, typically. And sometimes I just fall asleep early. Because I've been waking up early in the morning. So, but yeah, I'll be sure that tonight I get it uploaded. Yeah. Yeah. Okay. So that's consequent. You're stressed too. How's the study going? You started your studies at?
Yeah.
Yeah. That's very soon.
Yeah.
All right, so Jonathan's here. Good day, Jonathan. I can see that you've just come in, so we're just waiting until you came in.
Oh, appreciate that.
Can you hear
Thanks.
okay?
I can. Can you hear me?
Okay, yep. Now I might turn on the speakers a little bit higher so that I can be sure to hear you.
Okay.
That was a little bit inaudible, but
How's that?
hang on, try again.
How's that?
Yep, that's loud and clear.
Cool. Excellent. Thank you.
Thanks. Okay, so basically, Jonathan, what we're doing is just kind of going over some problems that Yoni gave us as practice for your quiz 3. So I'll go over the first few, and then Walla will come and talk about the second few. All right, so let's begin then. Okay, so the first question is on completing the square for matrices, or so it's titled in a book by someone, and I've forgotten their name because sadly I was in a little bit of a rush to grab the information I needed to prepare for the session. So I didn't see either the name of the author or a book, but this is in a book by an author. All right, so I'm sure you know about how to complete the square for a one variable quadratic function. So this is on matrices. All right, so first we've got a D by D matrix with real entries in it, and we're going to assume that it's symmetric and invertible. And we've got an X and a B. I put B as uppercase because there's another B in a subsequent question that I don't want to confuse with this one. Okay, so they're column matrices of length D with real entries. So the claim is that these two expressions are equal. Okay, and so to keep this on the same line, I've introduced another letter here. So Z is X minus the inverse of M times B, and it appears there and there. Okay, so how we're going to proceed is we're going to look at this one, Z transpose M times Z, and then we'll see what we get. It's a rather large expression once expanded out, but then we relate it to the rest of the terms here in this line. Okay, so beginning with that, and I'm not writing, incidentally, Jonathan, because there's much to cover in this episode, and I've got to give time for Walla because Walla also has a lot to cover. So I'm just going to go line by line with things I've already written down. Okay, so first we look at this one, Z transpose M times Z. And so I sub it in here. That's just this one that I introduced there. So we've subbed this in. Now we want to pull the transpose inside, which we can do. So then it's just X transpose minus M inverse B transposed, and the rest is the same as above. Now I want to apply that transpose on these two, but remember to do so, I've got to flip it around, right? In other words, the transpose of A times B is B transpose times A transpose. Okay, so doing that, this is what we have. And next what we want to do is basically take that transpose inside and or swap the order of the transpose and the inverse, which we can do as well. Right, so I pulled the transpose inside the bracket and the inverse symbol on the outside. But the point of doing that is that since M is symmetric, M transpose is equal to M. And so really this is just M inverse. Okay, but yeah, that's not what I did next. Okay, so what I did on this line is basically multiply the M through. So I expand this part of the bracket, so mx minus b, because m and m inverse multiply to give the identity. And so that just gives us minus b there. Okay, now we're going to apply that swap around and observation that this is just m inverse. Hang on, I didn't do that next either. Okay, no, so next we're going to multiply these two brackets and get 4 terms. Okay, so that's X transpose M times X, and then X transpose times minus B, which is this one, and then we multiply these two, and then we multiply this and this. Okay, so that's what we have, and now at this point we can make the observation that M is symmetric, and so this is just M inverse, and this is just M inverse. So now we have these 4 terms, because this here is M inverse times M. Yeah, okay, so right, so this one here is minus B transpose times X, so that's there, and then this one here is this one, but next we want to note that these 2 things are the same. They look a bit the same, right? They've got the same letters in them. They're just in a different order with transpose on different letters. Okay, but the observation that you should make here is that this is just a scalar in brackets, right? So we've got 2 scalars here. So that means that since they've got the same letters in them, and they're really just dot products, right, of two vectors. And so you can swap that around. All right, so these are the same, and so essentially we have two of these there. So that gives us that Z transpose MZ is equal to this three-term expression. And at this point, we can begin to compare with up the top what we have here, okay? So all we have to do now is rearrange. So we take this one on the far right to the left-hand side, subtracting. And so that gives us Z transpose M times Z minus B transpose M inverse times B is equal to X transpose MX minus 2 B transpose X. Okay, so this is a result that we're going to use in the next task. All right, so moving on to the next question then. All right, so now consider the least squares minimizing of this. Now, B here is not the same as the previous B, and so that's why I've made the other one uppercase, because we need to use that formula in this here. So basically, our task is going to use the expression in the previous formula to express the square of the norm of AX minus B. And so this is going to involve the pseudo inverse. All right, so we begin with the norm of AX minus B. Now that is just AX minus B transposed times AX minus B. So what we do next is we bring the transpose inside the bracket, and we've got to swap these two around because we're applying the transpose on the product of A times X. So we have X transpose A transpose minus B transpose there. Okay, now we can expand that out and get 4 terms. So that is X transpose A transpose times A times X. So this one times this one. All right, and next we take this one times the minus B here, and we get minus X transpose A transpose B. And now we take minus B transpose and multiply it by AX, and we get this one. And finally, we've got 2 minus signs here, minus B transpose times minus B, which is plus B transpose B. Okay, so next we note that these two here are scalars, right? Because AX is going to be a column matrix, and so we're multiplying this by the row B transpose. So this one's a scalar, and since this is the transpose of this, this is a scalar too, and it's the same scalar. All right, so we've basically got 2 of these there subtracting. So now we have 3 terms. Okay, continuing, what we want to do is emphasize putting brackets around the A transpose A, and this one right here, which is A B transpose transposed. Okay, and now we are in a position to use the identity from the previous page. And so I should pull that up right now. I've got it folded here. I'll put it above. So what we've got here is, so we want to identify this one with this, and this one with this. So in brackets here we have, we'll call that M. So this is M in this formula, and this one, A transpose B, is the uppercase B in the formula. All right, so good. So that means what I want to do here is replace this with this. And so you can see it's going to get a bit bigger. All right, but that's what we're going to do here. So we'll take these two and we'll replace it with this expression in the next line. All right, and so I've marked out in red what is what, right? So this is our Z right here, which is A minus the inverse of M, right, which is A transpose A, times our uppercase B, which is A transpose B, and then that's all transposed because it's in this part of the formula. And then we've got M, which is A transpose A, and then we've got the same expression but without the transpose. So this is Z transpose MZ. Okay, next, in our formula, we have minus B transpose M inverse B. And so subbing in the relevant terms here. So this is our uppercase B right here. This is our M. This is our uppercase B. So that's all of that, which matches the formula. Okay, so this one and this one. And then this part is just carried from the above line there. Okay, so we've got all that now. And now we've got to simplify this. So I'll put this page away and continue. Alrighty, so next we want to observe that this here is the pseudo inverse. Okay, so we've got the pseudo inverse there. So this gets a little bit more manageable to look at. It's still transposed. We still have this one, which was M. And then we've got the pseudo inverse in there as well. And then we've got a rather big matrix here, which is this, well, when we swap that around and apply that transpose. Okay, so we have A, and then this inverse, and then A transpose. So we want to give this a name to make this look simpler. Okay, and so that name will be the projection matrix. So we let P be this one, which is all this stuff up here, projection matrix, and then we can fit it in fewer lines. Okay, so we're nearly there. What we have to do next is turn this around. Okay, so in other words, express this as B transpose B minus B transpose PB, and then start factorizing out the B transpose and the B. Okay, so that's the last thing to do here. So we do exactly that, swap that around, factor the B transpose on the left and the B on the right. Remember, you've got to keep these, in terms of multiplication, you've got to keep the order as is. You can't swap around because you cannot assume that the multiplication commutes. Okay, now what we've done is we've shown that the square of the norm of AX minus B can be expressed in this way in terms of the pseudo inverse and the projection matrix. Okay. Now, continuing on, we've got another problem. So we'll put this aside for now. Have a look at the next one, which is to show that A transpose A is positive semi-definite. And so this one is rather simple. Basically, we use the definition of positive semi-definite, which is to, well, we must show that for all X that are column vectors with real entries, X transpose A transpose A times X is greater or equal to 0. Okay, so we begin with this expression here and look at it in a different way. Okay, so we've got X transpose A X, and then we move the brackets over because we've got associativity of multiplication, and then we observe that this X transpose A transpose is AX transposed. And so here we've got an AX, here we've got an AX, this one has a transpose on it, but we now need to observe that this is the norm squared of AX. Okay, and since this one is just a scalar, we've got the square of a scalar, and so that's a positive real number or 0. Okay, so it's, in other words, it's greater or equal to 0, and so we have shown that this one is greater or equal to 0, and so the matrix A transpose A is positive semi-definite. Okay, all right, now I'll go on to discuss the next question, which will be my last question before passing it on to Walla. Okay, what are the eigenvalues of I minus P, where P is the projection matrix? So I should note that on this page too. P is projection matrix. So the way I want to view this is by looking at the expression, the determinant of the matrix that I want to take the eigenvalues for, minus lambda times I, where lambda is or represents an eigenvalue of the matrix I times P. Okay, so I want to look at this expression equals 0 and then solve for lambda to get the eigenvalues. Okay, so now you've already done some of this in your lecture with Yoni by looking at the eigenvalues of the projection matrix. So basically what I've done here is I've just rearranged. So this is minus P here, and I didn't need to sub that in, but I did. So this is minus P, which is right there. And then I'm taking the two parts that have the identity matrix in it, and I'm basically factorizing out the identity matrix. And so what I have is lambda minus 1 times I. And if you expand that out, you have minus lambda I plus I, which is just these two right here. Okay, so the reason to express it in this way is so that we can say, aha, this is the eigenvalue of this matrix right here, right? When we have equals 0 on the right-hand side. Okay, so essentially we've got this equals determinant of minus P minus mu I equals 0. And I'm just saying, let's let this one here be mu, which will be the eigenvalues of minus P. Okay, now at this point, how do you compare this to the eigenvalues of P? Because you've already calculated the eigenvalues of P. So you could factorize out the minus 1 in this expression, which would give you a plus right here, right? So you'd have two minuses essentially. So you'd have minus mu there, but outside the front you'd have minus 1 to the power of n, right, where n is the size of the matrix. Okay, but since you have equals 0, you can multiply throughout by minus 1 to the power of n. And so essentially what you find is that this relates to the eigenvalues of P. Okay, in other words, these are the eigenvalues of minus P, the mu, right? And where we say mu is lambda minus 1, just from that expression. Okay, so yeah, so the eigenvalues of minus P are minus the eigenvalues of P. And since in lectures you have calculated that the eigenvalues of P are 0 and 1, we just have the minus of these as the eigenvalues of minus P, and so that's 0 and minus 1. Okay, so in other words, mu, the values of mu are 0 and minus 1. So then, solving this equation for lambda, we've got 0 equals lambda minus 1, and solving gives lambda is 1, and then minus 1 is lambda minus 1, so that gives us lambda 0. So in other words, the eigenvalues of I minus P are 0 and 1. Okay, and the last thing I have to show you is some Julia calculations, which are right here and I've written on this page. Okay, so so the first thing we've got here is, so I'll go through this line by line, using random. Okay, so these are the packages that you're loading and linear algebra. And so the first one initiates a seed, right? So you want to use a seed for the random numbers that come out of the calculation. So what that seed does is it allows you to repeat those experiments and get the same numbers essentially. Okay, so here we have n is 3 and m is 5. And so we generate a 3 by 5 matrix there, it looks like. And then B is a column containing 5 entries, okay, random entries. And so that's B right there, which is the last one out of it. Okay, next, so x hat is the pseudo inverse times B. So in other words, just this. X hat is the pseudo inverse times B. Okay, so that's a built-in function there. And so it returns that calculation, that product, which is just this. All right, and then next, the cost is the square of the norm of A times x hat. Remember, x hat is this one, minus B. All right, and so the cost of least squares is B transpose times I minus P times B, which we know is greater or equal to 0, since we deduced previously that I minus P is positive semi-definite. Okay, so this holds for all vectors x, where we put x as B there. All right, and so we can see, yes, we get a positive number for that one. And these two agree. All right, so I think I'm ready to turn it over to Walla. Are you ready, Walla? All right, so thanks. Grab my stuff. Sit down.
Yeah, okay, thank you.
Stand up.
Stand up. Yeah, it's good for me. Yeah, now we need to move to part E. In part E, they ask, find the sum of two quadratic forms. We have f of x equal x minus mu transpose multiply with sigma inverse, multiply with x minus mu plus x minus theta transpose times v inverse x minus theta. So we need to expand the first part and we need to expand the second part, then we need to add it up together. Let's try to expand the first part. We have x minus mu transpose times sigma inverse times x minus mu. The first step, we have x minus mu, all of it transpose. We can write it as x transpose minus mu transpose. So this is, we can write it written as x to power t minus mu transpose multiply with sigma inverse times x minus mu. Now just we need to expand. You will get 4 different items. Here we have x transpose times sigma inverse times x. This is the first one. X transpose sigma inverse times x. The second one, x transpose times sigma inverse times mu minus x transpose sigma inverse mu. Then we have here mu transpose times sigma inverse times x minus mu transpose sigma inverse x. And the last thing, mu transpose times sigma inverse times mu, because here negative times negative is positive, plus mu transpose sigma inverse mu. If you look here, this item and this item is the same because it consists of vector transpose times a matrix times a vector. So you can add this one with this one together. So we can simplify and write it as x transpose sigma inverse x minus 2 mu transpose sigma inverse x, okay? Plus the last items here, mu transpose sigma inverse mu. We need to follow the same step and expand the second part here. If you try to expand the second part, you will get x minus theta transpose times v inverse times x minus theta. This is equal x transpose v inverse x minus 2 theta transpose v inverse x plus theta transpose v inverse theta. Now we need to add it up these together. If you look here, we can add it. We can add the first one here with this one, because here we have x transpose sigma inverse x, and here we have x transpose v inverse x. So we can write it as x transpose multiply with sigma inverse plus v inverse times x. And if you look to this item, you can add this one plus this one together. We can write it as minus 2 multiply with mu transpose sigma inverse plus theta transpose v inverse, and all of it multiply with x, plus the third item, we can keep it the same, plus mu transpose sigma inverse mu plus theta transpose v inverse theta. Okay, we can call it this one as M. So we can write this one as M. So we can suppose that M equal sigma inverse plus V inverse. And we can write B as the transpose of this part, which equal sigma inverse mu plus V inverse theta. Just you need to take the transpose of this part, and R is a constant, is the last one. R equal mu transpose sigma inverse mu plus theta transpose V inverse theta. Now we can use the formula which you proved in part A. This formula said if we can write X transpose mu times X minus 2B transpose X. You can write this one and you can expand it by this formula. So if you try to write our formula here, you will get this is equal of X equal X transpose mu X minus 2B transpose X plus R. This is a constant, the last part. And we said that this part is equivalent, this one is the same as what we get here. So just we need to expand this part and write it as this is equal to X minus mu inverse B transpose times mu times X minus mu inverse B minus B inverse, sorry, B transpose mu inverse B plus R. So this is the sum of two quadratic forms, okay? If you need to find the sum of two quadratic form, you will get this answer. Is it clear for you? Okay.
Lala,
Yeah.
the link you sent, the file you sent,
Yeah, I sent
that
a link.
was
We will discuss this, the last thing, after I finish the second question. We need to look.
oh, that's okay. That's for the third question.
Yeah, the third. We will look to question 3.
Okay.
Now let's move to the second question here. The second question they ask: let f of xy equal x squared divided by y to power 4 for any x greater than or equal to 0 and y greater than 0. Find the Hessian and prove that for any xy, the Hessian matrix is positive semi-definite. If you try to use Julia code and try to plot this function, you will get, yeah, this is the Julia code. Here using plots package, and you need to use the grid so you can split in many numbers, and you define the function f of xy, and after that you try here to draw this function. If you look here, this function is convex function, and all the time it's an increasing function. Now we need to find the Hessian matrix for this function. Okay, we need to find the Hessian matrix. To find Hessian matrix here, just we have two variables, x and y. The Hessian function here equal, the first item is the second derivative of this function with respect to x. Here we have the derivative of the function at the beginning with respect to x, then with respect to y. Here also we have the derivative of the function at the beginning with respect to y, then with respect to x. This one is the same. And the third one, we need to find the derivative of the function, second derivative with respect to y. We have this function, just we need to find the second derivative with respect to y, the second derivative with respect to x, and the first derivative and second derivative at the beginning for x and then for y. If you try to find the derivative, you will get that Hessian matrix here equal, the first one is 2 over y to power 4. The second items, you will get minus 8x divided by y to power 5, and you will get here minus 8 x divided by y to power 5. And the last thing is 20x squared divided by y to power 6. This is the first part. We need to find the Hessian matrix, and we found it. Now we need to prove that this matrix is a positive definite. So we need to use the definition for positive semi-definite. If you have a non-zero vector, we can prove that it's a positive semi-definite if we can prove that X transpose times the matrix A times X greater than or equal to 0. Instead of matrix A, here we have the Hessian function, and we need to suppose that this X is not equal to 0. Suppose that the vector X here is X and Y. So we need to prove that here we have the vector XY multiply with the Hessian matrix, which we found it here, which equal 2 over y to power 4 minus 8 divided by y to power 5. And here we have minus 8 y to power 5 and 20x squared divided by y to power 6. And all of these multiply with x and y. Just we need to simplify. Just we need to simplify and find the multiplication between these three different items. If you try to simplify, you will get that this is equal to 2x squared divided by y to power 4 minus 8x squared divided by y to power 4 minus 8x to power 2 divided by y to power 4 plus 20x squared divided by y to power 4. Now just we need to add it up. Here we have 20 plus 2, it's 22 minus 16. This is equal 6x squared divided by y to power 4. And we know that x squared is all the time is positive and y to power 4 all the time is positive. So this value all the time greater than or equal to 0. So we can prove that the Hessian matrix here is positive semi-definite because it's greater than or equal to 0. Okay, this is second part. Now we can move to question 3 from the link, PDF file. I will discuss with you part A and part B. Okay. In question 3, they ask, we consider now the least squares problem, where we attempt to solve the linear system of equation A omega equal B, with A and M times N matrix and B and M vector. Consider the loss function. They give you the loss function L of omega equal the norm of A omega minus B squared, where the norm is the L2 norm, and we are seeking omega that minimizes L omega. So they give you the matrix A, it is M times N matrix. They give you B is M vector, and they give you the loss function, which equal to the norm square, and this is an L2 norm. We're looking for to minimize this function. In part A, they ask, explain why the minimizer of L omega is the same as the minimizer of the norm of A omega minus B. So in part A, we need to explain why the minimum point for L omega is the same as the minimum point for the norm of A omega minus B. Let's try to prove together. Here we have, this is question 3, part A. They give you that A omega equal B. They give you that A is M times N matrix and B is M vector. And give you that L of omega equal the norm of A omega minus B squared. We need to prove that the minimum point, prove the minimum point for L omega is the same as for the norm of A omega minus B. At the beginning, we need to suppose that the minimum point for L omega, call it omega star. So suppose that omega star is the minimum point for L omega. Let omega star is the minimum point for L omega. The minimum point for the function L. So we call that the minimum point here is omega star. Because it's the minimum point, so loss function of this point is less than or equal L omega. So L of omega star less than or equal L of omega for all omega belong to Rn. This is the first step. The second step, we need to try to write this function, L omega, as a composition of two functions. Suppose that we need to write L omega as a composition for two functions like G and F. So we can write L omega as the function of G of F of omega, where F of omega is the norm of A omega minus B and G of U equal U squared. If you look here, we have F omega, which is the norm, and the norm all the time greater than or equal to 0. This is greater than or equal to 0. And also we have GU equal U squared, and U squared is a monotonic function, which means all the time it's an increasing function. In addition, this function is continuous function. So G of U is a monotonic function, and it's also a continuous function. It is an increasing function and continuous. So we can find the inverse of this function. If GU equal U squared, you can find the inverse of this function, and the inverse of U squared is the square root of U. So we can find the inverse of G. So we can find the inverse of G, call it GZ. So G inverse of Z is exist, and it's equal the square root of Z. G inverse of Z equal square root of Z. Now let's try to substitute here in L of omega star and L of omega by using the function which we define it here, G of F of omega. So we can write L of omega star as G of F of omega star. So this is equal G of F of omega star less than or equal of G of F of omega. And we said that G inverse is exist. So we can multiply both sides by G inverse. Just we need to multiply both sides by G inverse. If you multiply both sides by G inverse, multiply both sides by G inverse, we will get that F of omega star less than or equal F of omega. So F of omega star less than or equal F of omega. And we said that F of omega star, which equal the norm of A omega star minus B. This is equal the norm of A omega star minus B less than or equal the norm of A omega minus B. So this is the proof for to show that for the loss function which define for the norm of A omega minus B squared, the minimum point for this function is the same as for the minimum point for the norm of A omega minus B. The idea is that because we can write the function L as a composition of two functions, and we can find the inverse of this function. Okay, the idea is here because we can multiply both sides by G inverse. So we get that F of omega star less than or equal F of omega. This is explanation for part A. The last thing we need to discuss, part B. Question here, 3, part B. In part B, they ask, show that the gradient of L, this function, the gradient of this function is the gradient of L of omega equal to multiply with A transpose multiply with A omega minus B. So here they ask, show that the gradient of L omega equal to A transpose multiply with A omega minus B. The same thing, we need to write this function as a composition of two functions. So the first step, we need to write L omega as a composition of two functions. Call it here, for example, h of x, which equal the norm of x to power 2. Why we need to do that? Because it's easier for us to find the derivative. And we need to write this is h of x and g of x equal ax minus b. So we can write the function f of x, which equal h of g of x. For example, if g here is a function from Rn to Rb and h is a function from Rb to Rq. So we need to find this, we need to know this because we will use it when we find the derivative, and we need to use here the chain rule. Okay, now we can use the Jacobian matrix or the Jacobian formula to find the derivative. So we can find the Jacobian of the function f. We call it d of f. We can use here the chain rule to find the Jacobian also for this part. This is equal d of h of g of x multiply with d of g of x. Okay, this matrix here, d of f of x, from here, you can find this matrix is the q times n. This function here, it is q times n. And you can see that the Jacobian for h, because here we have h, it's a q times b. And the Jacobian for g, this matrix is p times n. Okay? Now we know that h of x equal the norm of x to power 2, and we know that the norm of x to power 2, we can write it as a summation. So we can write h of x, which equal the norm of x to power 2 as the summation of x squared. Okay? And we know that the Jacobian of a function x, this is equal the gradient of a function transpose. There is a relation between Jacobian and the gradient, and the Jacobian equal the gradient of the function transpose. If you look here and try to find the gradient for h, the derivative of h, the gradient of h, this is equal to x here. And the Jacobian of h, this is equal to x transpose. From here, you can find the relation. We need just to put transpose. And we get that g of x equal ax minus b. We can find the gradient for g of x, which equal a. And the gradient of g of x, which equal a. Now, just we need to substitute and find the gradient of L omega, which equal the Jacobian of f omega transpose. And because we defined that f omega is a function, composite function for h and g, we need to use this one to find the Jacobian here for f, which equal d of G omega transpose multiply with D of H of G omega transpose. Because here we have a transpose, I put here transpose, and also I put here transpose. To find the first part, here we have the Jacobian of G omega transpose, and we find here the gradient of Gx, which equal A. So just we need to put transpose. This is equal A transpose. For the second part, here we have the Jacobian of H of G of omega transpose, and we know that the Jacobian of H equal 2 multiply with this function transpose. This function here, instead of x, we need to put G of omega. So multiply with 2, and all of it multiply with G of omega transpose, and all of it transpose. The first transpose is from here, and the second transpose is from here. And transpose, it gives you the same G of omega. So this is equal to times A transpose times G omega. G of omega, here, G of omega, we define G of x, which equal AX minus B. So G of omega equal A omega minus B. So this is equal to A transpose multiply with A omega minus B. This is the proof for the second part. For the third part, you can try to understand it, because I sent to you a PDF file. Try to look to part C. Thank you, Jonathan, for coming.
Thanks, Walla. Thanks, Sam.
Thanks, Sam.
Great. Okay.